We're now going to what seems like taking a step backwards, and we're going to revisit this concept of linear independence and introduce an object that will, in the future, actually be very useful for us. And this object is called a Wronskian. It's named after a mathematician with the last name Wronski, so we just call it the Wronskian. So suppose we have the following initial value problem, right? And it's going to look pretty familiar. So we're going to have our a2 of x times y double prime plus a1 of x times y prime plus a0 of x times y is equal to 0. And then we'll have some initial conditions. So let's say y of x0 is y0 and y prime of x0 is y0 prime, right? Something like that. Or actually, maybe what we can do, instead of using a prime there, let me just say something like y1. There we go, right? Now, if you notice, I've gone back to the case where we don't necessarily have constant coefficients because that's actually not needed for what we're going to do. So we're going to develop a theory that's a little bit broader than the cases that we know how to solve right now, right? The nice thing about the superposition principle, it still holds even if we don't have constant coefficients. Having constant coefficients, we've now developed a procedure for solving these second order wholies, right? But it turns out, even if we don't have constant coefficients, the theory still holds. So if y1 and y2, right? So y1 and y2 both satisfy the DE, then by the superposition principle, y equals, and I'll write it like this, c1 times y1 of x plus c2 times y2 of x also satisfy the differential equation. So also satisfies the DE, right? So we, again, provided we can find these two functions, right? And we know all possible linear combinations of those two functions will satisfy the differential equation. Then let's think of how we would go about trying to figure out the particular solution, right? This is where we would use our initial conditions. So using the initial conditions, what do we have? So let me plug in the x value on this side first. So I would have c1 times y1 of x0 plus c2 times y2 of x0. That would be equal to y0. So we would have that, right? And then, in order to apply the other condition, I need to use the derivative. So I would have, so let me say that this is equation 1. Then I would have to differentiate this, right? So y prime is equal to c1 times y1 prime of x plus c2 times y2 prime of x. And then that gives me another equation. So plug x0 in on this side. So I will get c1 y1 prime of x0 plus c2 times y2 prime of x0. And then that would have to be equal to y1. And I'll call that equation 2. So what we actually have here is a system of equations. There are two equations, two unknowns. I don't know what the c's are, but the y1 x0 and the y2 x0, those are numbers. And similarly, y1 prime of x0 and y2 prime of x0, those are numbers. So actually, I can sort of rewrite this in my standard form for a linear system and say, okay, here's the coefficient of the first variable in the first equation, and here is the coefficient of the second variable in the first equation, and then this would be like my constant on the right, like the b term on the right. And then do the same thing for the second equation. I would have y1 prime of x0 times c1 plus y2 prime of x0 times c2, and that would be y1. So we could actually express this system in matrix form, right? So in matrix form, the coefficients are y1 of x0, y2 of x0, y1 prime of x0, y2 prime of x0. My unknowns are c1, c2, and then my, b's, if you will, or the constants on the right-hand side of the linear system is y0 and y1. So now, our goal, remember, when we're solving for a particular solution to our initial value problem, we want to get one and only one solution. So the question is, what would guarantee this linear system having a unique solution? Well, think about it. The theory of linear systems says if your coefficient matrix is invertible, right, then the system must have a unique solution. So let's call this, like we do in linear algebra, let's call that A. So if A is invertible, right, we are guaranteed a unique solution for C1 and C2. A unique solution for C1 and C2. Well, what guarantees a square matrix being invertible? Well, the determinant of this matrix would have to be not equal to 0. So this implies the determinant of the matrix y1 of x0, y2 of x0, y1 prime of x0, and y2 prime of x0. This would have to be non-zero. This quantity here, right, what's the determinant of the coefficient matrix? This is what we define as the Wronskian of these two functions, the y1 and the y2, right? So we define this determinant as the Wronskian of y1 and y2. So here is the notation for it. So we're going to use the letter W for Wronskian, and then in parentheses you would put the y1 and the y2, like the two functions. Now, if you want to definitely indicate that this will be a function of x, right, you could put like of x there, and then that would be the determinant. So what I'll go ahead and do now is to drop the of x0 part, since I'm just saying that I'm going to keep it in terms of x here, and just say put the two functions in your first row, and then the derivative of your two functions in the second row. So like that, right? And then we know how to compute this, right? We know how to compute the determinant of a 2 by 2 matrix. So let's go ahead and write it down. So the Wronskian for these two functions is this y1 times y2 prime. That's multiplying essentially your a and d, and then minus y2 minus times y1 prime. And that's the Wronskian of these two functions, provided they both satisfy that differential equation. So this is y prime, right? So that's the Wronskian. So what does this mean now in terms of linear independence? Well, remember, if your determinant, again, and we stated it up here, if your determinant is non-zero, then you'll have a unique solution for that system, and then these functions are guaranteed to be linearly independent, and they will form a fundamental set of the solution of your Holdy. So let's actually state the theorem now. And then what we will do is go back and look at the functions that we identified for our three cases previously, and then use the Wronskian to show that they are in fact linearly independent, right? And so let's state our theorem first. And a lot of this, again, as you can see, is based on work that was done in linear algebra. The difference now is that we're working with functions. So let y1 and y2 be two solutions of the second order Holdy that was given above, not necessarily with constant coefficients, but obviously it works with constant coefficients too, on an interval, let's call it I, right? And it could be some interval of existence, right? Then the functions, right, y1 and y2 are linearly independent on this interval if and only if the Wronskian, so y1, y2, if that is never equal to 0 for every x in this interval. So for all x in I, right? So this if and only if is wonderful for us, right? It's good for us because it's a necessary and sufficient condition. But the thing is, we would have to start with two functions that satisfy the differential equation. So we can't just pick two random functions, right? We would have to first make sure that they satisfy the differential equation. Then once we do that, we can check our Wronskian to see is the Wronskian ever equal to 0? And then since it's never equal, if it's never equal to 0, then we can conclude that the functions are linearly independent, and therefore they form a fundamental set or basis for our solutions, right? So let's go through and look at case 1. So I'm not going to write down the auxiliary equation or anything like that, but for case 1, we got these two functions. We got e to the m1x and e to the m2x with the condition that m1 and m2 are real and not equal. So m1, m2 are real numbers, but they're not the same, right? So they're not different. I'm sorry, they are different. So they're not the same. So now let's compute the Wronskian for these two. So if we take y1 prime, that's going to give me m1 e to the m1x. y2 prime is m2 e to the m2x. So the Wronskian for this y1 and this y2, right? We can use the DET, or we could just go ahead and use the vertical bars for a determinant, which I will use. So it's the determinant of e to the m1x, e to the m2x, and then m1 e to the m1x, and then m2 e to the m2x. So using our 2 by 2 formula for our determinant, we'll have the product of these two. So this is, so I'll put the constant first. So it's m2 times e to the m1x, e to the m2x, and then minus, and then what will we have? m1 times e to the m1x times e to the m2x, right? So, of course, we can simplify these exponentials. So this is m2, and then I'll have e to the m1 plus m2x, and then minus m1, same thing here, e to the m1 plus m2x. But we have the same exponential, right? We have the same exponential. So what we have here is m2 minus m1, that quantity, times e to the m1 plus m2x, right? And what do we know about this? Well, let's think about it. This factor, because it's of the form e to the some power of x, right, is never equal to 0. So this is non-zero. And because m1 and m2 are different, this difference is also non-zero, right? So the product of two non-zero numbers, so that this Wronskian, no matter what, as long as m1 and m2 are different, which is what case 1 requires, for all values of x, it doesn't matter what x is, this Wronskian is never equal to 0. And I'll just say for all x in R. Therefore, we're guaranteed that these two functions, right, they satisfy the differential equation. That's how we came up with both of these kind of educated guesses. But now our Wronskian is telling us, yep, they are indeed linear and independent, and they form a basis, right? So this shows that works. Let's take a look at case 2. So case 2, that's when we had the repeated roots, and we had to use D'Alembert's procedure, and we came up with these two functions. So y1 is e to the mx, and then y2 is x e to the mx. All right, we had to multiply. We ended up multiplying by this extra factor of x, right? So again, let's see if in fact these work. And what the Wronskian is. So I know differentiating y1 will give me m e to the mx. Now for y2, I have to use my product rule. So I will have e to the mx plus mx e to the mx. There we go, right? So now let's set up our Wronskian. So the Wronskian for this y1 and y2, it's the determinant, and we'll have the e to the mx, and then I'll make this a little wider since this first derivative has a couple terms now, so I'll have x e to the mx, and then e to the mx plus mx e to the mx, and then over here we have m e to the mx. So that's the determinant that we have to compute, and we have to simplify and see if it can ever be equal to 0. So again, using our AD minus BC, so this times this, I have e to the mx times the quantity e to the mx plus mx e to the mx minus x e to the mx times m e to the mx. All right. Okay, so what do we have here? So let's distribute this e. So when I multiply these e's, I have to add the exponents, but that gives me e to the 2mx because I have to add them. And then same thing here. When I multiply the e to the mx times the mx e to the mx, I'll have mx and then e to the 2mx. Again, adding those exponents. The term that I subtract, I have mx e to the 2mx. So what happens is these two terms get canceled out, and I'm left with e to the 2mx. Again, because I have an exponential function, exponential functions can never be equal to 0, again, for all x. So it means that these two functions are always going to be linearly independent, and they will form our fundamental set. So we are justified in doing what we did for case 2. Well, that's good to know. I'd be, shocked if we were doing something that we're not allowed to do. So let's look at in case 3, where we have our complex conjugate root. So for case 3, remember our y1 was e to the alpha x cosine of beta x, and then our y2, I put my 2 there, y2 is e to the alpha x sine of beta x. Now, again, this is going to get messy because, first of all, we're going to need the product rule, right, for both of them. So let's give ourselves some space. So y1 prime is alpha e to the alpha x cosine of beta x, and then minus e to the alpha, or actually there's going to be a beta. Let me put the beta in front. So when I differentiate cosine of beta x, I'm going to get a negative beta, but I'll put that first, then I'll put the e, then I'll put the sine of beta x, right? So that's the first derivative of y prime. Let's look at the first derivative of, that's the first derivative of y1. Let's look at the first derivative of y2. Similar pattern. Differentiating the first, you're going to have your alpha e to the alpha x times the sine of beta x, and then plus, because when I differentiate the sine now, I'll have plus beta, and then I'll put the e, and then the sine becomes the cosine. All right. So it's a bit messy, but let's set up the Wronskian now for these two functions. So y1, y2. So it's the determinant. And I'll write the columns first. That way I make sure I'll have enough room. So I'll have e to the alpha x cosine of beta x. And then this term here, alpha e to the alpha x cosine of beta x minus beta e to the alpha x sine of beta x. And then for my second function, e to the alpha x sine of beta x. And then let's finish our second row, second column, alpha e to the alpha x sine of beta, and then plus beta e to the alpha x cosine of beta x. All right. So again, it's messy because of the need for the product rule for both terms. But let's see what we can do. So if I take this times this, there's not much I'll be able to do. So let's do it term by term. So let's take the e to the alpha x times cosine beta x times this term, and then times this term. So times the first term, we're going to have an alpha, and then I'll have to add the exponent. So I'll have e to the 2 alpha x, and then multiply the sine and the cosine. So this will be cosine of beta x sine of beta x. So that's taking this term, multiplying this term, and then do the same thing. Take this term and multiply this term. Well, this is a little bit easier. I'll have the beta, and then I'll have e to the alpha x times itself. So again, adding the exponents will give me e to the 2 alpha x. And then I'll also have cosine times itself. So that will give me cosine squared beta x. All right. So that's what I get by doing my A times D. Now let's do B times C. So take this function, again, multiply the first term. When I multiply the first term, what do I get? I'll have an alpha. So, and remember, this is a minus now. So I'll have minus alpha e to the 2 alpha x. And then I have to multiply, again, the cosine and the sine terms. So cosine beta x sine beta x. And then when I have, now remember the minus sign in my determinant calculation, when I distribute it, will make this a plus sign. So this will be plus, and then I have beta of, what do we have? So we have beta of, again, e to the 2 alpha x, and again, sine times itself. So sine squared beta x, right? Now, if we look closely, the terms that have both cosine and sine, they get canceled out because of the minus, right? Because look, they have all the same factors. We have it here, we have it here. We have this, we have this. We have the cosine, we have the cosine, we have the sine, we have the sine. So all that in red goes away. So that's great. What do we have left then? We have a beta 2, so here we go. So beta, where are we? Yeah, so we have beta, and then e to the 2 alpha x. Those are common factors, and then if I factor that out, I'll be left with cosine squared beta x plus sine squared beta x. And look at that. There is our Pythagorean identity coming to our rescue. This is always 1, right? So the Wronskian works out to be beta e to the 2 alpha x. So now we have to ask ourselves, can this expression, in this case 3, ever be equal to 0? Well, we know the exponential factor is never equal to 0. What about the beta? Well, let's step all the way back to where the beta came from. It's the fact that, remember, the roots of the auxiliary equation were those complex conjugates, alpha plus or minus beta I. Now, and this comes about because the discriminant of the auxiliary equation is negative. If that discriminant of the auxiliary equation or characteristic equation is always negative, then it means beta can never be 0, because if beta is 0, it means you wouldn't have a complex conjugate pair. You would only have the real part. So you would end up having something like actually case 2, where you just have the repeated root, right? So since the discriminant, your b squared minus 4ac of the auxiliary or characteristic equation is negative, then beta cannot be equal to 0, right? So that condition, having a negative discriminant of your auxiliary equation, it forces you to have this imaginary term. That's why we had to end up using that fancy result from Euler. So we know that beta can never be 0, and we know our exponential function under no circumstance that can be 0. So that's always non-zero. So the Wronskian in this case, again, is never equal to 0 for all real values of x. So every fundamental set that we've written down is justified, and our solution is guaranteed to exist for all real numbers. So the interval of existence for our second order whole's, right, is the entire real line. If you think of the functions that we end up getting, the e's, the x times the e's, the sine and cosine, those are functions that are continuous for all real values. So it all comes together, but the Wronskian is this specific tool that we can use to test if we know that the functions satisfy the differential equation. We can apply this test to give kind of a rigorous proof that the functions are in fact linearly independent, provided the Wronskian is never equal to 0. So there you go, a little bit of linear algebra sprinkled in with your calculus. That sounds like a good meal to me. So partake and feast away. I'll see you in the next video.